Hello, welcome everyone. I'm Sofiane Iblisdir, I work here. I'm professor at the department FQA. And it is my great pleasure to introduce Carmen Bañuls today, who's present as a professor in the teaching in the European Tensor Network School. And we're very pleased that Carmen accepted to give us a talk, the first colloquium of the year at our institute, ICC. And she will tell us about tensor networks, from quantum information to quantum field theory. Carmen was born in Valencia. She studied there, right? Mm-hmm. She's the holder of 2 PhDs, actually, one in physics, high energy physics to be more precise, and another in computing, informatics. So she was actually ideally placed to be working in tensor networks and all possible applications. Carmen is the recipient of various awards. She's been awarded the annual Extraordinary Degree Award in Theoretical Physics, the second National Award to the degree of Physics. She's been awarded the Academic Profit from the Conselleria de Cultura, Educación y Ciencia Generalitat de Valencia, and she's also a recipient of the Spanish Order of Civil Merit, 2015. Carmen has over 60 publications, given over 60 talks, and in a variety of fields ranging from high energy physics towards applications of quantum information techniques such as tensor networks to many-body localizations and so on. So without further ado, the floor is yours. Thanks for being here.
Thank you very much. Well, thank you very much for the very nice introduction. Thank you all for being here, and especially thank you for the invitation to participate in this colloquium. It's really great to be here in person and to be able to tell you about this work. So yeah, as Sofiane said, I'm working in Tensor Networks, and this has a lot of applications. The aspect that I want to talk about today is how this field connects to applications that, in principle, one could think are very remote, like problems coming from high energy physics, and in general problems of quantum field theory. So I'm not talking only about my work. I want to give you a bit of a perspective, but I will mention, of course, works that we have done, and this has been done in collaboration with many people, mainly with Ignacio Cirac, in whose group I'm working at MPQ in Garching, and well, with the support of our excellence cluster, MCQST. But as you will see, we have many collaborators coming from different fields, and this is what makes this so exciting, that we can apply these techniques to many different fields. Okay, let me see. Does this work? Okay, sorry. No, okay. So what I want to tell you today is what these tensor networks are, and if you are interested, well, many of you already know because you have been there. There is now an ongoing school in the next building or near building in the Parc Scientific about precisely what these tools are. Well, now it's a bit late because it's almost over, but there's still some interesting talks and sessions to happen. Anyway, so if you just want the moral of the story, tensor networks are ansatzes, so guess functions, if you want, to describe the state of quantum many-body systems that are based on entanglement. And well, they are not only there if you want, not only that if you want, so they have appeared in different contexts, but for our interest and for the topic of the talk today, the context that we are interested in is quantum many-body systems. And the idea here is that you have a system made out of a number of individual constituents, this capital N, and each of them has a physical finite dimension, meaning that it could be, for instance, a spin 1/2 particle that has a two-dimensional Hilbert space, right? So this dimension we typically call with this small d in like our descriptions. So you have a system of this kind of quantum particles, and they have some kind of interactions, and this might describe an effective model of some problem of interest to you, or it could even describe now what happens in a quantum computer. And well, these particles are interacting with each other, and what we want to do is to describe some states of this system. Typically, in physics, we look at equilibrium states, either ground states or thermal equilibrium states, but of course, we want to go beyond that. We are also interested in things like dynamics and out of equilibrium. And then, well, let's say that we want to describe interesting or physically interesting, physically relevant states. And well, what is the problem? The problem is that even if we know what the particles are, what the interactions are, and each of these particles has a basis, well, of course, we can write an arbitrary state of the Hilbert space of this system by just writing a superposition in a given basis, which is a tensor product of the individual bases of the constituents. But the problem here is that the number of coefficients we need to do that grows exponentially with the number of particles in our system. And this is this number that appears here, this d to the n, is the number of coefficients that we will need to describe an arbitrary state in this system. In the tensor network field, we use very often a diagrammatic representation for this, for our algorithms and for describing the problems. And this is basically representing tensors graphically as objects, in this case boxes, with a number of legs. Each of the legs corresponds to one of the indices of the object. So what this means is that if we consider all the coefficients all that we need for this state, this is, in our language, an n-leg tensor is just a multi-dimensional array, so it's an object with n different indices. And graphically, this is just a box with n open indices. So if we want to describe this object, this is exponentially expensive in the number of pieces in our system. And the idea of tensor networks is that instead of considering the most general coefficients that have this arbitrary tensor structure, we consider ones that only have a reduced number of parameters. And the way to achieve that is to consider coefficients where there is a certain structure to this tensor. And this structure is precisely that of a tensor network. So this is what this plot here, this graphic here represents, which is a number of different tensors. You see you have here a number of smaller tensors, and they are connected in some way. And this connection means contractions. I will explain in a second. And the open indices should be the same. And the idea is that when you contract this thing together, this will give you all the coefficients you need. But of course, not all the states will have this structure. So you're sort of restricting the family of states that you consider to some with a particular property. So going back to the diagrams, just to explain a little bit more in detail, as I said, a tensor for us is just a multidimensional array. There is no transformation property assigned to where the indices point to, for instance. And this is, for instance, an arbitrary example with 8 legs. And if I would just assign one value to each of the indices, this would be one component of the tensor. The whole tensor is like all the possibilities together. So that's my tensor. And joining tensors together is the same as contracting. So the simplest example is a matrix-matrix multiplication, for instance, that we would represent in this case in this way. So you see the first tensor here is a matrix, it's a tensor with 2 legs. So an object which has 2 indices, this is a matrix, the second one 2. And when I draw them joined together, what this means is that I'm taking a sum over products of components with a common index. So basically, it's the same thing as a matrix multiplication. So this is what the diagrams mean when you join 2 tensors. So you should ask, okay, this seems like a very big restriction of the amount of states that we could have to those that have precisely this structure. So why should this be useful at all? And the idea is that we don't look for arbitrary states in the Hilbert space. We are interested in states that appear naturally, typically states that solve some physical problem or are related to some physical system. And people refer to that as the relevant corner of the Hilbert space. Because the idea is that a state at random in the Hilbert space can have a lot of entanglement. It's very far from the easy products, the easy states, which could be product states. But the states we're interested in are not that general, so they do not have that much entanglement. And a way to make this more concrete is precisely what happens with ground states of local Hamiltonians. So ground states of local Hamiltonians usually satisfy what is called an area law of entanglement. So an area law is just a property that tells us that the properties of a region of the system depend not on the bulk of the system or on how big it is, but they are given just by something that happens on the boundary of the system. So in this case, for instance, we have here a two-dimensional system, just as an example, and the property that we are interested in is how much entanglement you have between one region, for instance, one interior region that I'm calling here A, and the rest. And the area law tells us that instead of depending, so the entanglement between both of them is given or measured by the entanglement entropy, which is basically the entropy of the reduced density matrix for this region. So instead of being as large as the number of particles that you have in here, which is the scaling that you would have in a random state, the area law tells us that this entropy scales only as the number of sites on the boundary. So as in this case, in a two-dimensional system, is of course a perimeter, but you can think of this in any dimension. That's what this is called, an area law. And well, while this is observed for Hamiltonians in 1 and 2 dimensions in condensed matter problems, it's rigorously proven only for the one-dimensional case and for local Hamiltonians with a gap. So for this, there is actually a mathematical proof. So this restriction that the Hamiltonian has a gap, of course, is not true in critical systems. But it turns out that for critical systems which violate this condition of the theorem, the corrections to the area law, so they have more entanglement than the area law, but the corrections are very small because they are only logarithmic with the size of the region, which means that they are still very little entangled compared to the arbitrarily chosen state in the Hilbert space. And moreover, for equilibrium states at finite temperature, this kind of area law is satisfied for any dimension at any finite temperature for local Hamiltonians. Only in that case, the quantity to look at is not the entropy, because the entropy in that case is not what measures the correlations between one part of the state and the other, is the mutual information. But it's a measure of correlations, which so gives us the same conceptual information, if you want. So this is sort of the motivation why it makes sense to concentrate our efforts in states that have a particular property. And this property is, okay, they have a structure of entanglement that we know how to represent efficiently. But there are different families of tensor networks. They have different shapes. So especially interesting are those ansatzes that satisfy the area law just by construction. And this is the case of what are called matrix product states and PEPs, and I will present them in a second. But this is not the only possibility, and I will also try to mention that. So matrix product states are the best understood. They are like the paradigmatic example of tensor networks, the best understood family, whose formal properties, mathematical properties are also very well understood, and for which we have very efficient algorithms with which we can do numerics with very good precision in a very wide number of problems. So the idea of a matrix product state is the following. So in the picture that I presented before, we consider the general state of the Hilbert space that would look like this tensor with n legs, and this is the general case. So the restriction for matrix product states consists on states or tensors that have precisely this structure that is depicted here. So the coefficients of the state of the system can be computed as a contraction of a number of tensors, one per site in our system, which are connected in a linear manner. So we have sort of a chain of tensors, one per site. And this ansatz is also called tensor train in some other context, not in the quantum many-body, but well, you can immediately see why. Right? If you look at the expression that you get for each of the coefficients, it's written down here. When you select one of the coefficients in the bases, so that would be one value for each of these open indices, well, when you select one value, you don't have an open index anymore, and then what you are left with is a contraction of these objects which have at most two legs. So it's basically a contraction of matrices, hence the name of matrix product. And well, this ansatz satisfies the area law by construction, because the amount of entanglement that you can put in the ansatz is limited by precisely how big this dimension that you have between the matrices is. So this dimension is called the bond dimension. We can make it larger or smaller. If we would make it 1, then we would reduce our ansatz to a product state. if we make it larger than 1, because, okay, let me just stop here. So to see this, you can just see what this expression is if the bond dimension is 1. If the bond dimension is 1, instead of matrices, you have just vectors. They only have one open index because this is just numbers. So when we fix the values of each of the physical indices, what we have for the coefficient is just a product of numbers. So basically, this is the same as having one vector per side, and this is just a product state. So if you go beyond that, you make matrices that are larger than 1 times 1, then you can include more states. And how much entanglement you can have, say, in half of the system is limited precisely by how big this bond dimension is, but not by, so it's not influenced by how large the part of the system you are cutting is, because it's really mediated by this link. So the way it works is that it is, so this entanglement entropy that I was saying before measures how much entanglement you have between one half of the system and the rest, for instance, or one part of the system and the rest, is upper bounded by the logarithm precisely of this dimension. And this is very easy to see, although I don't have time to show you the details. But okay, this is a one-dimensional answer. One can use it also for two-dimensional problems and for actually general problems, because it's general enough, but the bond dimension you would need would grow fast if you want to do two-dimensional problems. But they have a natural generalization to two dimensions, and this is what is called PEPs. And the picture is, you can see that this is an immediate generalization of the tensor picture before to something that lives in two dimensions. You still have one tensor per side, and they are joined with one of these virtual legs to the neighbors in the lattice. Of course, you can construct one thing like that in any lattice of any geometry. This is not restricted to 2D, not restricted to square lattices. You can put this on any graph you want, one tensor per side with one open index, which is the physical index, and the connection between the tensors follows the geometry of the lattice on which you want to put it. Well, in the case of this particular picture, this also satisfies the area law by construction. I say in the case of this particular picture because one could also think of very non-local graphs where to put things and define cuts in a different way. But say that you think of this planar graph, and then you cut a region in here. Well, as before, the entanglement that you include between one part of the region and so one part of the system and the other will be limited by how many of these legs you are cutting. And this is precisely the boundary, the size of the boundary of your region. So these are the ansatzes, matrix product states and PEPs, that satisfy the area law by construction, but they are not the only ones. And I said before, well, tensor networks are not necessarily this. They are just they follow this entanglement-based construction, but this is a particular structure. So there are other ansatzes that have different scaling of the entanglement, at least or especially in 1D, because they were constructed to reproduce precisely this exception that I mentioned before to the area law that happens in critical systems, so that they can describe exactly or scale exactly as the critical 1D case. And this is the case of trees. Well, here I have an example of trees and Mera, which were proposed by Guifre Vidal in the early 2000s. And I'm not talking about this anymore, but these are also, they have another, especially Mera, another focus of interest, or they are another focus of interest for people coming from, again, a very different field, because it has been suggested that they could be a discrete representation of the ADS-CFT correspondence, and people also from the holography community have started looking at their properties with this idea. I'm not talking about that. I don't know much about the topic, but I think this is also interesting aspect of tensor networks that doesn't have to do much with the numerics I'm telling you about today. Anyway, so tensor networks, and in particular the families I'm focusing on, which are these matrix product states and PEPs, have interesting properties, and they have been studied also from the formal point of view. And in particular, matrix product states and PEPs have this property that they are complete families, meaning that if you make the ansatz large enough, if you make the tensors big enough, you can describe any state you want in the Hilbert space. So you can always increase the number of states you include in your ansatz and check the convergence of your solution, for instance, if you are doing numerics. there are also good reasons to argue that they are good approximations for equilibrium and ground states of local Hamiltonians. And this is very related to disentanglement properties and this area law that I was describing before. Also, one can define these families, although my pictures mostly are finite. You can define these families directly in the thermodynamic limit. So you can directly study a system which is infinite and actually work with basically one tensor that gives you the properties of all the system. And this is also very useful from the formal point of view to understand the properties of the states that come out of this construction. And well, any state of this form that you can have is actually the exact ground state of some Hamiltonian, which is local. But that's more of a formal, also mathematical property. So another very interesting thing from the point of view of using them for any problem is that they can be combined with symmetries. And the idea here is that if you have a state that is symmetric under a global symmetry, and a global symmetry means that you act with some transformation on each of the, so here is a unitary transformation of some group, but this can also be more general. On each side of your system, you want your state to remain invariant or to transform in a well-defined manner, but let's say that it's invariant. So, well, one can see that if you take tensors that are well behaved under the symmetry transformations, and in particular, that they transform under proper, say, representation of the same group element for each of the legs, then you have an ansatz which is invariant. So if you, especially if you think of the translational invariant case that I was drawing before, basically you have one transformation and it's adjoint in one direction and another one in the other direction. When you join all the tensors together and you apply this transformation on each of the tensors, well, the transformations on the virtual indices will cancel each other and you get immediately an invariant state. So basically, if you use tensors that are invariant, you construct an invariant state. But for matrix product states and PEPs, it's even stronger than that because there is an if and only if. So if a state is invariant, and it's one of this family, you can actually find a representation with invariant tensors. And I showed the picture for a global symmetry, but one can also gauge the symmetry and construct PEPs for gauge symmetries. And there's been a lot of work in this direction, and yeah, I'm not talking about these formal results, but this can also be exploited to do numerics for systems with the particular symmetries. Anyway, what I want to talk about today is mostly about how we do numerics with this ansatzes and how we apply these numerics to solve problems that are inspired by something very different or questions that come from field theories. So we have a number of algorithms available for these tensor networks, but in a very simplistic manner, we could say that there are two big groups of algorithms. One of them is we can minimize the energy of the ansatz in a variational manner. So basically, we have a Hamiltonian which has some kind of locality, and I'm not entering too much into the detail, but let's say that the Hamiltonian has itself the structure of one of these tensor networks that I was drawing. So if we have this, then we can guess that our ground state is of the form, say in here is the one-dimensional case, but this also works for the two-dimension, just the pictures are easier in this way. So we can guess that our ground state is of the MPS form in this case, and then we can optimize what are the tensors that minimize the energy for a state of this form. And this can be used to find the ground state and to find the low-lying excitations of any given model, which has this form. The other big group of things that we can do is to apply some kind of local operator to a state of this form. So if you apply just a local operator on one side, well, this doesn't change the structure as a tensor network of the state. But if you apply something that acts on two sides, in general, you will get something where the dimensions of the tensors would need to change. So the trick of these applying operators is to reduce the effect of our transformations to, or approximate the effect by, again, a state within the family with finite dimensions or bounded dimensions that we are interested in. And this is useful to do different things. One of them is to do imaginary time evolution, which is like Euclidean time evolution. And it's used to either compute the ground state in an alternative manner, but also to compute thermal states. But also we can apply, so do this for the unitary evolution, and then we can simulate time evolution with this ansatz. And well, the picture would be something like that. So we apply something that has a structure, as I said, which we can fit in the tensor network scheme, and then we can approximate the result as a tensor network. This is not the only thing there is, so there are other algorithms also for time evolution, for instance, TDBP, but you could always think that also in this case, the result of evolving the state is reproduced or approximated by something with a, say, MPS structure. So basically, you see, we can compute ground states, we can compute excitations, we can compute time evolution, and we can compute thermal equilibrium states with these ansatz. We have the algorithms to do that, and in some cases, we also know when this works well. So, as I said, this works for MPS and PEPs, but there is a difference in how costly things are. And this is why, up to now, there are much more, many more results in 1D, and they are applied for many more problems than to 2D. However, they work for 2D, and the development in 2D is very fast. And actually, if you would visit some of the talks in the school, you would realize how much the field has advanced in the last years and how much we can do now also in 2D. So the main reason, so a bit more quantitative way, why they are different, or I think this difference in applications, is that computationally doing one dimension is much easier than in 2D. And well, the scaling of the algorithms in one dimension is given basically by how big the matrices in our ansatz are. And this, how big they are, is the bond dimension. I'm calling it capital D in here, which is unfortunate because I'm using also capital D for the dimensions, but I think from the context it's fine. So in the one-dimensional case, it scales like D to the cube, which is very moderate. So we can do very large bond dimensions, which means that because the family grows and grows to cover the whole Hilbert space, we can improve and improve or refine our ansatz and get better and better results. So for 2D, it scales on the also polynomially, so from the computational complexity point of view, it's still efficient because it's still polynomial. There are some subtleties in here that one has to take care of, but the main, say, I wouldn't say problem, but maybe difficulty or hardness of running these algorithms is that the scaling is, so as compared to D to the cube, is something that goes like D to the 10. And in these completely arbitrary units, you can see how a curve that scales like D to the cube goes as compared to one that goes like D to the 10. So it's much harder, you can do smaller bond dimensions, but still there are very good reasons why you don't expect to need very, very large bond dimensions for 2D. And although the algorithms are more cumbersome, there is a lot of advance in the last times, and you can see very competitive results coming from the PEPs community. Yes?
Why 3 and 10?
Well, I should draw the pictures for this, but it's basically the cost of the, so at the lowest level, the cost is given by how difficult it is to contract the tensor network to compute, for instance, what is the value of the energy. So if I'm minimizing the energy, I want to compute basically what is the value of the energy in my state. And for that, I have to put the state, which has a tensor network structure. I have to put the Hamiltonian, which also has a tensor network structure, and contract with the bra. And now I have something without open legs, but I have to find the result of this contraction. In the one-dimensional case, this is again a matrix-matrix multiplication. And I can just do it just with a bit of like care, D to the cube. In the two-dimensional case, it's very different, because to contract a two-dimensional network of tensors, I have to start somewhere, and then my intermediate contraction grows size is not a vector of fixed dimension D, it grows with the system size. So in principle, it's not possible to contract efficiently exactly the two-dimensional network. So the D to the 10 comes from approximate methods that approximate the contraction of the two-dimensional network by reducing it to something like a one-dimensional one. But it's basically the cost of having these tensors with a lot of connectivity, then they have many legs, and I have to somehow apply steps where I contract some of these legs, and some of them need to be left open because they will be contracted with other neighbors. There is not an equation, if this is what you are asking for, like what is the exponent of the... Yeah, there is a simple way. I mean, I should draw a picture maybe to this. Should I do that? Or maybe I can explain you later or show you a picture later. Yes?
The estimate of d to the 10 is for matrix product states or for any?
For PEPs into dimensions.
For PEPs.
I can put matrix product states into dimension, and then the cost will still be d to the cube. The problem is that the d I need to get the same precision for a two-dimensional problem. So if I'm trying to use the MPS ansatz for a two-dimensional problem, I can do it, but I need to scale my bond dimension up to a number that gives me a good precision. So the bond dimension I would need to get the same precision will grow with the size of my system somehow, exponentially actually. And then in principle I will need a much larger bond dimension also, but it will still be d to the cube. So I'm skipping a lot of details in here. When I say it's a complete family, of course, if I want to cover the whole Hilbert space, somewhere the exponential complexity must come in. So an arbitrary state of the Hilbert space I can also write as a matrix product state with a bond dimension d, but this bond dimension turns out to be exponentially large again in my system size. So for the numerics, what we are or in the problems we are concerned about, we are interested in situations where the ansatz is good for the, say, ground states, equilibrium states, and so. And this means that we can approximate very well the physics or the properties of the states that we are interested in with a moderate bond dimension, something that doesn't scale with the system size, or scales only slowly with the system size. But in principle, I can do 1D, and then it would be d to the cube, but the d would be larger. Oh, is there something else? No. Okay. Okay. So this is really the cost of contraction. So this is how things scale. Now, what happens with real time? So real time is really something that for many problems is very difficult to compute, especially out of equilibrium, right? And I told you, well, we have a way of doing real time. The problem with real time is that, as I said, in this kind of basic algorithms, what we are trying to do is to approximate the result of the evolution by a state of this form. And what if the physical state is not of this form? Well, this is precisely what can happen when we have out of equilibrium evolution. And actually, it is known that in non-equilibrium scenarios, the entanglement in our state, so the true one, can grow very fast. And very fast means that the entropy can grow even in the one dimension. This is known for very simple models. Well, actually, it's in the one dimension where we know the best results. It can grow linearly with time. The entropy can grow linearly with time. And this means that if we would want to represent our state with a matrix product state, our bond dimension would need to grow exponentially in time, which is, of course, something that we cannot do. This means that we know that it will work for moderate times and also for situations where the entanglement doesn't grow so fast, which might also be interesting. For instance, if your evolution is sort of quasi-adiabatic, or you are at low energies close to the ground state, and so on. But this is sort of the limitation. Anyway, there are different evolution algorithms. What I talked about is evolving the pure state, and well, the drawback is that if the entanglement grows fast, then this works for finite times. But one can also evolve operators directly. I'm not talking about this too much, but it's another possibility. And one can also try different strategies just to compute observables. But I'm also not talking about this further. So just to show you that there are a number of algorithms that one can use to explore this, even this out of equilibrium dynamics. And there are also or we work also in collaboration with Sofiane, precisely in other strategies that allow us to extract also information about what will be the non-equilibrium properties, but are completely different to this describing the state as a tensor network. Anyway, what I wanted to talk about mostly today is how to use this ansatzes for problems which in principle come from quantum field theory. And well, the first natural scenario where to try these things has been, of course, lattice gate theories. This is a very logical step because what I told you about is that tensor networks give us a way to solve a Hamiltonian, and they're actually a non-perturbative way of solving these Hamiltonian problems. For one dimension, these algorithms are extremely successful. This is really like the state-of-the-art methods for strongly correlated problems. And for higher dimensions, the developments are very fast, and for some problems, they already outbeat the results from especially in situations where other methods like quantum Monte Carlo have a limitation. These tensor networks are already producing like the best results available. And they work, as I said, for ground states, low-lying excitations, thermal states, and time evolution with the caveat that I just described. On the other hand, lattice gate theories are also, or were also introduced as a non-perturbative way of solving quantum field theories, but they work in a very different framework, right? So they mostly use path integral formalism and then Monte Carlo. Of course, the algorithms in there are very developed, and they are very powerful and can work with four-dimensional lattices of very large system, very large size compared to the sizes of our tensor networks. The kind of problems you can compute in there for which this works includes spectral properties, finite temperature, but they have problems in some scenarios where the same problem appears and the Monte Carlo doesn't really work. And this includes a finite density, which is for us a chemical potential, and also time evolution. So it makes sense to try these alternative methods to attack precisely these problems where the Monte Carlo is limited and we cannot get answers from there. And also, it makes sense to learn about these problems and about techniques from the advanced lattice gate theory, or lattice QCD actually, algorithms. So how do we use tensor networks for lattice gate theories? Well, it's basically the same we do for quantum many-way physics in general. And there are different possibilities. One of them, I mentioned in passing, that there's a more formal approach, which basically focuses on the properties of the tensors, or characterizing the properties of the tensors to characterize the properties of the state, or to understand what kind of states you can construct with tensors which have particular, for instance, transformation properties. And this has been done so it's basically based on what are the symmetries in the tensor, and as I mentioned before, this has been done in particular also for gate symmetries, and then there are prescriptions how to construct these PEPs ansatzes with particular gate symmetries, and for instance, Luca Tagliacozzo has worked a lot on these things, and also other people. But this is a very formal or a more formal constructive approach to the tensor networks, not the aspect that I want to talk about, I'm talking about today, which is that of numerical simulations. So numerical simulations have the advantage as compared to other numerical methods that we don't have a same problem in these tensor network contractions. There are different ways of using the tensor networks still to do this kind of computations, and let me mention that one possibility would be to attack the partition functions directly, which is closer to the standard approach of a lattice QCD calculation, and use the tensor network to describe the partition function of the model or the observable that we want to compute. And then try to find ways of approximate this contraction and find its value. And this has been worked on by different groups now, but I'm not talking about this topic. If you are interested, there is a relatively recent review by Yannick Maurice and co-workers. And these kind of approaches that I try to contract the tensor network of the partition function are in general called as tensor renormalization group approaches. But there are many different algorithms which look at the details of how this works or not. Then the other approach that I'm really focusing on today is to use the tensor network to describe the state. So to use the ansatz to describe the relevant states that appear in the problems that correspond to this situation. So the general strategy is that, first of all, we need a Hamiltonian, because these algorithms work for a Hamiltonian. So we need to define a Hilbert space and how the Hamiltonian acts on that. So we need to choose the proper basis, because this ansatz is for a given basis, and it's related. So how good it is related to the basis being the proper one. We need finite dimensional degrees of freedom, and this is sort of opposite to the problem otherwise for, say, things like Monte Carlo, because fermions have no problem for that. They just are occupied or not. So, and we don't have a same problem in our case. But the gauge bosons, in principle, do not fulfill that property, so one has to do something with them. And usually, or one of the most used approaches would be to truncate them, so to truncate the occupation number of the bosons, and then one needs another parameter, so take care of another parameter in your simulations to see that this is not affecting the results. In 1D, one can also integrate them out and then solve directly in the physical subspace. And well, there is another approach, which is looking directly at models where you don't have infinite dimensional gauge bosons, you have the symmetry, but everything is finite dimensional. And these are the quantum link models introduced by Uwe Wiese and Chandrasekaran in I don't know, in the 90s. So one interesting thing that I'm just again mentioning in passing is that these ingredients are actually the same if you think of quantum simulating these models in a lab. So if you have a lab of, say for instance, cold atoms, and you want to engineer a Hamiltonian that corresponds to one of these problems, you basically have to think of these issues and decide a way of dealing with all of them. And this is the reason why there is a close connection between the development of tensor network methods for these problems and the proposals for quantum simulations. And in many of these papers, you can see this connection, because most of them are proposing schemes to simulate in the lab some of these gauge models, and they do the calculations with tensor networks. Of course, from the point of view of the computational physics, one would like to take these tensor networks and attack lattice QCD in 3+1 dimensions and solve something like thermalization or something like that. But this is very far, right? So to see if this makes sense at all, one has to go step by step, and this is what has been done in the last years. And one starts with a one-dimensional case. So there are some couple of reviews in sort of 2 years ago describing the efforts, also including the ones about quantum simulation, if you are interested in the details. But just briefly, there were some early results, already attempts to attack this, even with the early formulation of the DMRE algorithm. I'm not really stopping, but say let's say that there were already results showing that the MPS ansatz, at least for one-dimensional lattice gauge theory, was a very good one, because it produced very good results, very precise results. But this was sort of isolated effort, and then in the last years, there has been a more coordinated or collective effort to approach the problem in a more systematic way. And this starts with like the simplest model one can consider in one dimension. This is the Schwinger model, which is basically QED in 1D. So it's some electrons interacting with photons, but only in 1D. And here there is a number of references. It's not comprehensive at all, but just for you to see that many groups, and of course we also have done that for the last, I don't know, 8 years or so, or since 8 years, have worked on the different aspects that can pose difficulties to attacking the problems with tensor networks. And it's been shown that one can do precise equilibrium simulations, and actually that also the quantum simulation approach can be feasible. I'm not, I will show a few examples now, but I'm not talking very much about the details. So if you're interested, again, you can look at maybe some of these review works. So beyond the simplest case, one can introduce other aspects that appear in more real, if you want, problems that also are difficult to solve for Monte Carlo. And the first one is something like finite density. So in that case, the Monte Carlo has a sign problem, and this can also be attacked by tensor networks. One step beyond is changing the gauge group and doing something non-abelian, which is more difficult, but it's also been tested. And this has also been done including dynamics, like string breaking. And of course, the next step is to go beyond one dimension. And this is, as I said before, it's harder, but there are already works going to 2+1 dimensions. And I will also mention a bit of this. And even very recently, there's been a work published by Magnifico and co-workers where they actually have the same, the first simulation using tensor networks for a 3-dimensional problem, which again is QED and a finite system size and some restricted ansatz. But this is already showing the power of the ansatz. So for the one-dimensional case is where the exploration has been more systematic. And just to give you an example, so these are some of the things that different groups have tried with different properties of the ansatz and so on. For instance, the spectrum, this has been done with a lot of precision with the objective to extract the continuum limit, as you would do in a lattice QCD calculation. And so the case of finite density has been done in different models, like the Schwinger model, SU1, but also the SU2 and SU3 quantum link models. And well, what people have done in here is to explore the phase diagrams of the model. And a very useful maybe characteristics of this tensor network ansatze is that you can access things that maybe are not so easy with other methods, and one of them is the entropy. So the entropy in a gauge theory is something, is an interesting, in the ground state of the gauge theory, I mean, in the lattice, is something interesting, because the entropy of entanglement is related to what is the concept of locality, and what can you do, or what can you not do if you are restricted to operations that are only local, say, on part of the system. But if you have a gauge constraint, those are not purely local, because they link, say, two physical sites where there is matter through the gauge link between them. And this makes this thing interesting, and it is known how, for say, the continuum limit, the entropy has to behave. It's known that for a massive quantum field theory, when you discretize it and then take the continuum limit, the entropy will diverge in a particular manner. Well, this can be seen numerically with the tensor network simulations. I'm not talking you, if you are interested, or any of you is interested, I'm happy to give you more details. But these plots just show that just by extracting, looking at the entropy of the answer that you got as an answer for the ground state, you can actually extract this kind of divergence without knowing it, and get the value of the central charge corresponding to the model. So one very interesting thing, and it's the last one I'm showing it here, is time evolution. Time evolution is more difficult, so it's not been done up to the continuum limit yet, but it's been done close to the continuum, and it's been done in out of equilibrium. For instance, different groups have looked at string breaking phenomena, simulating them in different models, and also the Ghent group looked at so an out of equilibrium, say, Schwinger pair production in the infinite limit at values that are also very small lattice spacing. So this is not the pure continuum limit, but it's relatively close, say, to that. And you can do with these methods something that is not possible with other simulation methods in a regime which is totally out of equilibrium. So of course, the next step is going beyond one dimension. And this sort of we understand how to do. I told you one knows how to construct gauge invariant PEPs. One can also restrict the ansatz to some particular PEPs where you can do some calculations more efficiently. And with this, and also with other restricted tensor networks, there are some results. But if we want to do this kind of continuum extrapolation and so on, we also should look at, okay, the unbiased, say, simulation with the general powerful PEPs. And in principle, we have all the ingredients that we need to do this calculation, but it's sort of even harder than one of these nearest neighbor models in condensed matter, because not only there's the computational cost and the bond dimension that we might require, but there is also the presence of plaquette terms in a two-dimensional lattice gauge model that makes things more complicated. Well, recently, and I'm just going fast, so how much more time do I have, by the way? Because I didn't see when I started. 5 minutes? Okay. So I'm going fast, but if any of you is interested about details of any of these works, I'll be happy to discuss them later. Anyway, so okay, this was just to show that very recently we actually looked at a way to deal with this so plaquette terms, which are hard in general, for one particular case, which is a Z3 gauge theory in an infinite lattice using the PEPs ansatz. And this is sort of like using the general PEPs ansatz, not putting any particular restriction. I'm not telling you the details about that, but okay, let me show the result. The result shows the different phases of the model. The model is known to have, in the ground state, a transition between a deconfined and a confined phase. And actually, in this case, we can explore what is the picture in the ground state, what is the map of where the electric flux is. And if you put external charges, which is what is shown in this little picture here. So this is where external charges are. You see that the electric field in this region is confined because it's only there. The rest is just empty. While in the deconfined phase with the same charges, the charges are shown here as yellow points, the field is sort of uniform. This is just an example. We can compute many more observables. Another approach is to just restrict the ansatz, as I said before. I'm just skipping this. There are many works using restricted ansatzes. And yeah, we have done also calculations with other, so I spent most of the time talking about lattice gate theories because it's where people have put the most effort, and there have been many works on different aspects exploring systematically what are the issues, but it's not the only problems that one can look at. One can also look at other quantum field models, and well, in our case, for instance, we've looked at the T-ring model, among other things, but I'm just skipping this example to mention something else. In this here, it's also a question about finding the ground state of the model by mapping it, say, to a spin model that at the end is the thing that we know how to simulate very efficiently with our tensor networks. And this is just the steps to make the connection, but this was not worked out by us. It was worked out in the 70s, how to map this model first to a Hamiltonian formulation and then to a discrete and spin representation in the proper way. And at the end, it translates to a particular model of spins, which is what we call an XXZ chain, with two kinds of fields. So it's not exactly solvable, but we can solve it numerically. And we can do simulations with up to 1,000 spins, for instance, and increasing one dimension. And then we can study how correlations behave. And we see how they behave in two phases. And you see that there are different curves. So like one thing decays in this way, and the other thing saturates to some constant. And this actually allows us to determine what is the phase diagram of the model as a function of the mass of the fermions and the coupling. And well, in this case, if the mass is different from 0, well, there is not much known about where the transition is, but okay, all this region in here is known now to be critical, while this one here is gapped. This is just with small lattice spacing. One could still try to do the continuum limit extrapolation. I'm just going a bit fast over this, but I want just to mention that maybe, okay, can I do this? No, okay, for some reason this doesn't work. Okay, then I'll just jump to the last example I want to mention. So other things that we have tried is to use thermal equilibrium states and evolution of them to identify the structure of singularities in a retarded correlator that for some spin model can be linked to a quantum field model. And actually this is interesting because in some quantum field theories it is known what the structure of these singularities has to be. In holographic theories this is related to these quasi-normal modes of black holes. And in CFTs it is known where some of these poles are at finite temperature. And we can do this numerically without knowing too much by just doing our tensor network simulations. So I'm just showing here, for instance, one of these complex frequency plot of where these modes are, and you can see in the real space this will be like the stable particles of the model, and they have some masses. In some cases, these masses are known. And when these particles are unstable, then they develop an imaginary part, and this is in good agreement with some predictions from theoretical calculations. So this is just another example. But there are other things that we can do, and I just want to mention this, that recently we were exploring this also in collaboration with Sofia, and I mentioned it before, how to look directly at the spectral properties of the Hamiltonian. So we can also use these tools and the algorithms that we have to explore something different, which is far from the ground state and far from equilibrium. And what we can compute in this way is something that is the density of states or some generalized version of that. And well, I'm not stopping to show that, just to mention that recently we applied this to, again, the Schwinger model, and we looked at two very different regimes for a finite lattice situation, where the density of states has very different structure. This was done by Irene Papastatio, who is a PhD student in our group. I'm stopping here, but I didn't talk about many of the aspects of tensor networks related to quantum field theory and high energy problems. So one of them is these quantum simulation applications. As I said, in these reviews you can see some of this progress. Another one is the approach as a partition function instead of an ansatz for the state. And again, I can refer you to some recent review by Yannick Maurice there. Another aspect is that one can define tensor networks also directly in the continuum limit. And this is some more recent development, but there will be a lecture tomorrow by Antoine Tillois in the Tensor Network School that is happening at the Park Scientific. So if somebody is very interested in continuous tensor networks, I would recommend you to try to go to that lecture. And well, finally, there is this aspect that I mentioned before, in which I don't work, but there is also a community working intensely on this connection between the tensor networks and the say, gravity or holography. If you are interested in these topics, I can recommend you to check this series of seminars. They are called Heptian seminars. The address is very complicated, so I didn't really bother to write it here. But if you look for the name, it will appear. It's organized by Michael Heller's group in Potsdam. And there have been a number of talks, and they are all available since more than 2 years ago now. And they cover these topics and many others, including the ones that I haven't covered today. So if you are interested in anything related to tensor networks and high energy physics, well, this is the place to look at everybody who has been working on that. So just to finish, the message of this talk is really that these tensor networks are an ansatz for quantum many-body systems based on entanglement, and that we have checked that they are feasible for the states that appear in lattice gauge theories and in many discretized quantum field theories. This has been tested very systematically in one dimension. All these things that I mentioned have been tried. And this is very related also with the quantum simulation proposals, which some of them have already started occurring. So there's already some experiments that have simulated a lattice gauge theory with cold atoms. And well, in 2 dimensions and higher, there's already progress and there are already results. I mentioned some very, very briefly some that we have done ourselves, but there is a lot going on. So, well, that's all, and thank you very much for your attention.
Thank you very much, Carmen, for this very nice and global presentation. We have some time for questions.
Thank you. So, in the first part of your talk, there was a lot of focus on local Hamiltonians, right? Locality in the Hamiltonian,
yes.
Right? Is that a full requirement? Is that something that you can get away with, or?
Yes, no, I mean, if your Hamiltonian is local, and by local, I mean it's short-range interactions, then typically you can express it with one of these tensor network structures, and formally, you have results that ensure that the ground state will be well approximated. This doesn't guarantee that your algorithm is going to find this approximation, but you have a full motivation. If it is not local, you can still run the algorithms. And in 1D, what people do is that because the algorithms are efficient and you can scale the bond dimension higher and higher, you can perform this scaling analysis and still extract the physics of many problems that are not local. Actually, for the 2-dimensional case, you can write a 1-dimensional ansatz that, for instance, wraps around some 2-dimensional system. And even though you will need, in principle, a large bond dimension to describe a system as it gets larger and larger, for some problems, this is still the best result available. By scaling the bond dimension and performing suitable finite size scaling, you can still get very good results. And this model is then not local because you stretch somehow the connections that we are nearest neighbors. So from the application point of view, it's not a hard limitation. It's the other way around. From the formal point of view, you have very good reasons to apply this to local Hamiltonians, but you are not prevented to do it for anything else.
I have a question about your comment on tensor networks applied to continuum theories.
Mm-hmm.
So my question is not about the details, it's a conceptual question. So in those cases, can you truly describe theories in the continuum, meaning there is really no ultraviolet cutoff? Or
Sorry?
can you really describe theories in the continuum, meaning that there is truly no ultraviolet cutoff? Or in other words,
there is a cutoff in the ansatz. So you have an ansatz which lives in the continuum, but if you try to apply it to relativistic theories, I'm not an expert in the topic, but you can identify a cutoff anyway. So you have an ansatz which describes your state in the continuum, so it gives you a continuum state in terms of finite dimensional parameters, which are matrices. But they can be understood as a continuum limit of one of these drawings that I was picturing before.
So you mean the lattice spacing somehow is going to 0, but you still have a UV cutoff in momentum or energy or something
you
like
get
this?
a cutoff, yes, if you apply it to relativistic theories. Yeah.
Okay, thank you.
In these applications to quantum field theory, no? I suppose there is some approximation. No? When you say you compute the partition function, for example, does Tensor Network give you the exact partition function, or is it an approximation? And what is the parameter that controls the approximation? Because you are restricted to a subclass of states, right?
Yes. So in general, you could think that the partition function can be represented exactly as a tensor network. This is true for many models. You could have also an approximation, but let's think that your partition function is exactly a tensor network. Now the problem is contracting this tensor network. Then your approximation is how you perform this contraction. So you approximate the contraction by, say, coarse graining your partition function, typically, contracting together several tensors and expressing that or approximating that by a smaller tensor again. So now you have coarse grained your partition function, and you have discarded some elements in your sum. So you need to increase the number of elements that you keep, if you want, the size of your tensors to improve your precision. And the question is, how big are the tensors you need to get precise results? There are different flavors of this coarse graining for different models, and people have tried different things, but this is sort of the general spirit of all these approximations. So the parameter would be how big the tensors are when you start coarse graining your partition function to then end up with, say, the trace of a single tensor where you have coarse grained it to a single point.
Okay, thank you.
Yeah, I couldn't get an idea from your presentation from the, let's say, the computational requirements that you need to reproduce some of the results, say, in the Schwinger model. I mean, there are models that can be solved exactly, and of course, you know.
Yeah, I don't think I have a plot in this presentation. I was thinking. Actually very small. That's why we say that the ansatz is very feasible. So I can tell you of our simulations of the Schwinger model. What we did was to look at the ground state and excited states, say, to find the vector and scalar particle. And in practice, we had a finite lattice, which meant that we were not restricting ourselves to the zero momentum sector. So we had to look at all the excitations and identify when we were changing, say, from the vector sector again to the scalar. So we are finding discrete excitations that give us sort of a dispersion relation. This is what we need to compute. Now, how costly this is means how large my bond dimension needs to be to get this precisely enough to then be able to do all the extrapolations to go to the continuum limit. So what we found is that bond dimensions of the order of 100, 150 were enough for system sizes of the order of 1,000 sites, and gave us as much precision as we wanted. So you have to think that from these calculations, you have to first be sure that you are converging bond dimension, then that you are converging system size, because our system was large but finite, and then do this for different lattice spacings and take the continuum limit. So we did all this, and then they do a systematic extrapolation in the continuum limit, and we got extremely precise results of like all these masses. And this was only with bond dimension 100. You have to compare this 100 to the dimension of the Hilbert space, or say the largest dimension that you would need, which is like that of half of the Hilbert space. And that would be 2 to the, what did I say, 2 to the 500 in that case. So extremely small. And you get still, at the level of one simulation, precisions of, I don't know, 10 to the minus 12 in the energy. And then you need this good precision because there are all these extrapolations to do, so that at the end you get a precision, I don't know, 10 to the minus 5 or something like that in the masses, in the continuum. It will depend, of course, on the model. It's harder for the SU2. We don't get to do so large systems and so on. But so the spirit of these studies was actually exploring whether the ansatz makes sense. Because if we see that it scales very badly, then it probably doesn't make sense to think that at some point we will be able to do much higher dimensions than 1. But this is not the case, fortunately. And for the PEPS simulation that I mentioned very fast, our 1 dimensions were only up to 5. And still, in that case, it's not the continuum, it's just a lattice simulation, but we can map the phase diagram of the model very nicely. So I think all these results are really not like the definitive ones, but they are encouraging towards like putting the effort in developing further these algorithms and say tailoring them for problems that are interesting. And these computations are done in normal computers, really like a normal CPU in a cluster of CPUs, no supercomputer or anything like that. Not even GPUs, so one can also use GPUs to speed up these things, but so this is all very, very doable.
Can I just make just a nasty question? Have you been able to derive any result that we didn't know before by other means?
Well, yes. For instance, this thing that I showed before, I hope this still works. I don't know. No, for some reason, I cannot leave this now. But OK, I can try to go back. So I was showing very fast these finite density results. So, for instance, the one here, this is just, it's sort of a simple case, right? So it's the Swinger model with several flavors and different chemical potentials for the different flavors. So the one that is here is actually the one that we can compare with the exact case because it's for massless fermions where there is an exact solution. For massive fermions, there is no exact solution, but we have a phase diagram also telling us where you have, in this case, is first order phase transitions that give you different imbalance of the 2 flavors. So for instance, this is a result already in 1D that you cannot get with Monte Carlo because the Monte Carlo only works for particular values or combinations of the chemical potentials. And the time evolution thing that I was showing before, although that was not in the continuum, was for a finite lattice. Again, for, say, strongly interacting case, where you don't really have a perturbative method or semi-classical method to approximate the results, the tensor networks was giving you longer times than anything else.
Yeah, another example is the TJ models, which in some regime is a good approximation of the Fermi-Hubbard model for superconductivity. PEPS computations beat fixed node Monte Carlo. This is
yes, of course. I mean, I was focusing on the lattice gate theory part, but indeed, in condensed matter, in 2D, there are cases where PEPs are now the state-of-the-art result for some of these complicated models.
Any other question? No? Well, if not, let us thank Carmen again.
Thank you very much.